This is the last lecture for assignment 3, and it just completes the respiration system. So we just did an anagram recap where I asked you to look at these terms and just try to reshuffle the words. So for example, the first one, viola L, that is alveoli. And these were the rest of the terms there. Okay, so we looked at diffusion first of all. And before we look into diffusion in any more depth, just want to say, obviously we need oxygen for energy. We need to remove the waste products during exercise, or just during general life anyway, but if we relate this to sport, we need to remove carbon dioxide as quick as we can as well. So the exchange, it occurs through something called diffusion. Basically what that is where particles move from a high concentration to a low concentration. Right. So what I mean by that is, I want you to imagine the lungs. So you just take a deep breath in. You've got a lot of oxygen in those lungs now. And all the blood up by the lungs has got a lot of carbon dioxide in it because it's just brought the carbon dioxide up from the working muscles. So we've got a high concentration of oxygen in our lungs and a low concentration of oxygen in our blood. So that oxygen is naturally going to move from our lungs into our blood. And the reverse is going to happen for carbon dioxide. So you've got a high concentration of carbon dioxide in your blood, whereas you've got a low concentration in your lungs, so they're going to switch over. And the easiest way to think about this is if you think of a sugar cube, that has got lots of sugar molecules packed into that cube, so that's a high concentration of sugar molecules. You drop that sugar cube into a glass of water, now the surrounding water has got a very low concentration of sugar. So through natural diffusion, the sugar molecules are going to go from the high concentration, which is a sugar cube, into a low concentration, which is dispersing through the water. Now, if you left that cube in there long enough, it would just dissolve and the sugar would just disperse throughout the water. You need to know the percentages we breathe in and out. So nitrogen is actually 79%. We don't use it in the body, so we breathe in and exhale the same amount. In terms of oxygen, there's 21% oxygen in the air. And when we exercise, or not even when we exercise, just generally doing things, we use 5% of that oxygen that we breathe in. Therefore, we breathe out 16%. With carbon dioxide, we breathe in 0.04%, we breathe out 4%. And that's because during the aerobic system, which we'll talk about for assignment 4, we actually produce carbon dioxide as a byproduct of that energy system. So we're creating carbon dioxide when we're actually creating energy for ourselves. Okay, so how can we improve diffusion rates? So obviously you want to get rid of the waste products as quickly as you can, and you want to get oxygen to the working muscles as quick as you can. So we want to improve that diffusion rate as quick as we can. There's a few ways we do that. We create a large surface area. So if you think about the lungs and how big they are and how we've got all those different bronchioles and all the different alveoli we talked about earlier, but then you have loads and loads and loads of capillaries in there as well. So the more capillaries we have across a massive cross-section of the lungs means more oxygen can get into the blood and we can get rid of carbon dioxide quicker. What we also want to do is get the distance between the capillaries and the alveoli as small as possible. Now, the smaller that distance, the quicker the oxygen and the carbon dioxide can be transferred. Think about in football when you're passing a football, or a netball when you're passing a netball. Obviously, the closer you are to someone, the quicker you're going to get that ball, and the further away you are, the longer it's going to take to get the ball. And it's just the same principle with the distance between the capillary and the alveoli and the diffusion of oxygen and carbon dioxide. Also, we need a slow capillary blood flow. Now, this allows something called complete oxygenation. So, think about if you had a hoop on the side of a rugby pitch, and you're sprinting as fast as you can past that hoop, and you go to pass the ball through the hoop. Now, you're not going to be that accurate every time because you're going so fast. Now, if you were to walk past that hoop, you're probably going to be very close to 100% success rate because you're nice and controlled and you can think about the pass. Well, it's the same with blood. If the blood goes slowly past the alveoli, this will allow for oxygen to transfer from the alveoli into the capillaries really efficiently, and also allow those carbon dioxide molecules to come out of the capillaries and into the alveoli, and it just makes the process much more efficient. If the blood was going through quick, some oxygen might not get out, and then you just got some carbon dioxide might not get out, and then you just got carbon dioxide going back around into your body, which is counterproductive and it'll just reduce your performance. Click on that picture, take you to a YouTube video. Okay, so we're looking at respiratory volume. So rather than put down a load of different formulas or formulae, I like to use a triangle. So what you basically do is cover up what you want to work out. So first of all, you need to know what we mean by these things. So if you click on this Quizlet link here, it defines all the different terms. But we're just looking at respiratory volume, breathing rate, and tidal volume. Breathing rate is the amount of breaths you take per minute. Tidal volume is the amount of air that's moved in and out of the lungs in one breath. Respiratory volume is the amount of air that is moved in and out of the lungs within 1 minute. So if I wanted to work out respiratory volume, what I would do, I would cover this up, which leaves me breathing rate and tidal volume. Now, because they're next to each other and this line by here is in between them, what we have to do is multiply them. So we would multiply the breathing rate by tidal volume to give us respiratory volume. However, if I wanted this breathing rate, I would cover it up. So what that would give us is respiratory volume over tidal volume, which equals respiratory volume divided by tidal volume. And there'll be the same process for tidal volume. Cover that up and it will give you respiratory volume divided by breathing rate. So if we look at respiratory exercise, so these are just average amounts. So the average person will have a tidal volume of 0.5 litres, the breathing rate of 12 beats per minute. So if we go back to our triangle, we want to know our respiratory volume. We cover up that respiratory volume. We know we need to do breathing rate times tidal volume, which would be 0.5 times 12 beats per minute. What that will give you is 6 litres per minute of air going in and out of the lungs. And it will just be the same principle for below here. So have a go at that yourself. I won't give you the answer for that. Try and work that out utilising the triangle. Some key terminologies we need to know about the lungs and lung structures. First of all, the thoracic cavity here is just the area behind the rib cage, and that's just what houses the lungs. Okay, so we need to know the structure of the lungs. So lungs are like very elasticated. They need to be elasticated. Just hold on to your chest now, take a deep breath in and out, and just feel your chest rising. Now, if lungs were not elasticated, they would not be able to expand as much as they do. They're divided into lobes, and the right is larger and has to accommodate the heart. The space is known as the cardiac notch. So if you look by here on this left lung, it's reversed like the heart, by the way. If you look at this left lung, you can see that notch there. So if I go back to the previous slide, you can see this here, this cardiac notch, which is housed in the heart, and you can see how the right lung is actually quite a bit bigger than the left lung. So the lungs split up into lobes. So we've got 1, 2, 3, and 1, 2 on the left. So 3 on the right and 2 on the left. Now the role of the lobes are, say you get an infection. So say you get a lung infection by here. Rather than shutting the entire right lung down, we're just going to shut down the inferior lobe on the right lung. This allows the rest of the right lung to function and all the left lung to function, which makes it much more efficient. If you had to shut down an entire lung, you wouldn't be able to get much oxygen in at all. However, by only shutting down one lobe, that allows the lungs to function as efficiently as possible. So we've got the pleural membrane and visceral pleura. Now these play a really, really important role. What they do, they contain pleural fluid, and their main job is to prevent the lungs from getting any friction and keep the lungs airtight. So the pleural membrane here keeps the lungs airtight, which is really important. When you're breathing in, you don't want any air getting out of your lungs. So think about a football, playing football with football. And if the football wasn't airtight, the air's just coming out of it and the ball goes flat, and you can't kick the ball as efficiently because you're losing air. Well, if you're breathing in air and it's just coming out of your lungs, it's not airtight, and you're just losing air, you're not going to be able to get that oxygen around the body. So it makes the whole respiratory system not as efficient as it could be. The pleural fluid. Now what this does is spread along the outside of the lungs. So it's very, very similar to the heart. We don't want any friction on the lungs. If it starts sticking to the rib cage and things like that as we're breathing as quick as we can, and it just sticks for a little bit, it stops us from being able to breathe as quickly as possible. We can't breathe as quick as we need to. We can't get as much oxygen into the body, to the working muscles. We can't get rid of that carbon dioxide as quick as we want to. Therefore, our performance will decrease. Last two things we need to know: breathing control. We've got two ways we control breathing. So we've got chemical control and neural control. So chemical control is controlled by something called chemoreceptors. Now, chemoreceptors detect chemical changes in the body. So if carbon dioxide levels increase, then breathing rate will naturally increase. So as I said earlier, the aerobic energy system has a byproduct, which is carbon dioxide. We actually create carbon dioxide when we're creating energy for ourselves. Therefore, if that carbon dioxide increases, naturally our breathing rate will increase to get in more oxygen and get rid of that carbon dioxide. And the other one is neural control. This is just where you voluntarily think of breathing yourself. So you can control your breathing. You can hold your breath now for 10 seconds if you want to, because you can decide when or not to breathe.